This is lecture 17 in network theory. Right? In this lecture, we are going to start network theorems. So in this lecture, I am going to discuss three, that is superposition theorem, Thevenin's theorem, Norton's theorem. Next lecture, we will see the maximum power transfer theorem. So in the previous lecture, in lecture 16, so we discussed Thevenin's theorem and star to delta transformation. So Thevenin's theorem is nothing but the algebraic sum of powers in a loop or in a circuit is becoming zero. Right? So also we have seen how to convert from star to delta transformation. That is, so I only discussed the resistances. Sometimes we may have the capacitance also, C1, C2, C3, etc. Right? So we have discussed the parallel combination of C1 C2. If C equivalent is there is a parallel combination. C1 plus C2 we can make, that is a parallel combination. And if it is a series, so C1 C2 by C1 plus C2 when it is in series. So opposite of the resistances. So same for this capacitances also will be the opposite we have to take. Right? So just see that, do one problem, you will get the idea about these capacitances. Right? Now, in the lecture we are going to discuss about these theorems. So first, this superposition theorem. So first I will read the statement, then we will discuss one problem, then it will be clear. So remember, in a linear network, it should be underlined, in a linear network, the response in a particular branch. Right? So suppose this is a some network. So if I want to find the current in this branch, right? Now that is how to find. So either nodal analysis or mesh analysis. Other way also it is there. In a particular branch resulting from a number of independent sources. So we are having two independent sources, may be computed by summing the responses to each individual source with all other sources made inoperative. That means at a time I will make operative as one source and another source we will make inoperative. That may be this is the current, so I will make 0. Right? When this is operating, this is made inoperative. If this is operating, I will make this is as inoperative. Then I will find two individual response, I1 and I2. Then finally we will add that summation, that responses we will add when we will get the overall response. So that is the superposition principle. In a linear network, the response in a particular branch resulting from a number of individual independent sources. Right? See, minimum 2 should be there. So maximum 3, 4, etc. So minimum at least we should have 2 independent sources. So number of independent sources may be computed by the summing the responses to each individual source. So each individual source with all other sources made inoperative. Now how to make inoperative, that we need to know. Right? Now suppose if we are having a voltage source, suppose we are having a some 2 volt voltage source. How to make inoperative means, so to make voltage 0, we need to do the short circuit. Remember, the short circuiting voltage source. Similarly, if you are having a current source, this is a 2 ampere or whatever. So to make current 0, we need to make open circuit. Right? So this is the open circuit to make current 0. If I made short circuit, the voltage will become 0. So this is how to make inoperative. That is, voltage is 0 means short circuit, current is 0 means open circuit. Right? Now we'll see one problem, that is the plus minus 5 volt, 1 ohm, 2 ohms, 3 ohms, and this is 2 ampere. So this is I. Now we use the superposition theorem, then we can find I. So if I use superposition theorem, suppose 5 volt source alone. So we have to make like this, 5 volt source alone. That means current source should be 0. So plus minus 5 volt, 1 ohm, this is 2 ohms, and this is 3 ohms. So I need to make inoperative. That means the current source is open circuit. Whenever this is open circuit, what is this current? 0. That means whatever the current is coming, it will be in this loop only. Now we can easily find I1. I1 is equal to, this is 5 by 3 amperes. So very simple. Next one, 2 ampere source alone. Right? that means the voltage source should be made 0. So that is short circuited, and there is 1 ohm, this is 2 ohms. Here I need to find I2, this is 3 ohms, and this is 2 ampere. Now again it's very easy. See, 2 ampere is coming here, and there is a 2 branches leaving. So we can apply simply current division principle, that is I2 is equal to main current 2 into opposite resistance 1 by total resistance 3. So it is 2 by 3 ampere. Now by superposition theorem, what is the total response? Summation of the individual response. So I1 plus I2, right? So what is this current? 7 by 3 amperes. Now if you solve this one by nodal analysis, we will get same answer, right? So that you can verify later. Now there should be some limitations. The first one is, so limitations of superposition theorem. So what are those limitations? We'll see. The first one is the network should be linear, right? Otherwise we cannot apply superposition theorem. Network should be linear, right? The second one is this theorem cannot be applied to measure power, right? To measure power. So when you are finding the power across any branch, so by superposition theorem, if I find P1 then P2, to find total power I cannot add P1 plus P2, right? So that is the important limitation. So we will prove this one now. The third one is it should have at least 2 independent sources. So the network should have 2 or more than 2 independent sources, right? Independent sources. So that is the 3 limitations we'll have, right? Now what is the linear circuit? So linear circuit, how can we say circuit is linear? If circuit has linear elements, so it includes, what are those? R, L, C values, independent current source, independent voltage source, and similarly dependent sources. Now in dependent sources we will have 2 types. One is linear and non-linear. So what are those linear? Suppose it is like this, plus minus some k into I is a linear. Similarly, suppose some plus minus k into V1 is a linear, right? Similarly, some k into I1 linear. Similarly, some k into V1 is a linear. See, the moment these proportionality constants are some linear, or we can say it is in power of ones, then it is a linear. Or this dependent element is V1, V2, so these are the linear elements. Suppose what is the non-linear is something like this, plus minus k into V1 square, right? See, this constant anything can be, but the moment these dependent elements are in a power of 1, we can say it is a linear. The moment it comes as square, right? Similarly, something like this, right? A into I1 square. Now these are the non-linear dependent sources. So whenever these non-linear dependent sources are there, we cannot apply the superposition theorem. But this linear dependent sources are existing, then we can apply the superposition theorem, right? Now we will prove that why we cannot apply the this superposition theorem for power calculations. Suppose in a network, suppose resistance is there and the across resistance current is I. So whenever current is I, what is the P1? So P1 is equal to I square into R, right? Similarly, there is a resistance, one more same resistance, R, this is R1, this is R2 suppose, and this is what, the same current, so different current, so I2, and this is P2 is equal to I1 square R I2 square R1 R2, right? If R1 is equal to R2 is equal to R, right? So what is P1? It is I1 square into R. P2 is I2 square into R. Now we cannot apply the superposition principle, so I can find I1 from this one, that is root of P1 by R. Similarly I2 I can find root of P2 by R, right? This is I2. Now by superposition theorem, what is I1 plus I2? So it will become root of P1 by R plus root of P2 by R. Now what is the total power? Our total power is I square into R. So what is I? So root of P1 by R plus root of P2 by R square into R. So I can cancel R because it's a 1 by square root, so it will become R. So it is root of P1 plus root of P2 whole square. So this is the reason why we cannot apply the superposition principle for the power, right? Depending on the current directions, we'll have plus or minus actually, right? If both current directions are same, then it is plus. If the current directions are opposite, it is the minus, right? Plus for same current direction, minus opposite current directions, right? So this is the reason why we cannot apply the superposition principle for the power calculations, right? Now we will see now the two important theorems again, the Norton and Thevenin's theorem. Thevenin's and Norton's theorem, right? So this is a dual, one is dual of another, right? Now if I know that Thevenin's theorem, then or Thevenin equivalent circuit, then I can know the Norton's equivalent circuit also, right? So in any given network, suppose we are having so many independent sources, so many dependent sources, something like this, some 2 volt, 1 ohm, 1 ohm, 2 ohms, 3 ohms, and suppose some 2 ampere, right? So many resistances, so it should be a purely resistive network, right? Now suppose if I want to find a current or response in this branch, right? Now what this Thevenin theorem tells you, that replace the remaining network, replace the remaining network with a independent voltage source and series resistance, right? So that is VTH and RTH. So wherever we need to find the response at that particular, so it is considered as simply load, and this should be same, that is 1 ohm, and the remaining circuit should be replaced by a series resistance which is RTH and a voltage, independent voltage source VTH. Then if I find the current here, this should be same as the we find for the using analysis, nodal analysis or mesh analysis. So this current should not be changed, right? So this current is always constant. So when we do either superposition theorem or mesh analysis, nodal analysis, and using this type of circuits also, right? So that is this Thevenin's theorem. The dual of this one is, if I apply the source transformation for here, so it will become, this is the IN, Norton current IN, and this is, I can replace simply RTH also, but I will replace by RN, and here same, the load resistance 1 ohm. So generally we say it's a network A, and this is network A as equivalent and network B as load, wherever we need to find the current. So this is the Thevenin's theorem, right? So remaining wherever we need to find, so there we will apply the same resistance, or we consider simply load, and the remaining circuit will be replaced by voltage source and series resistance, or IN and RN, right? So parallel current source and parallel resistance. So current source and with the parallel resistance. So this is Thevenin's theorem and this is Norton theorem, and these two are dual, right? So dual of each other, right? So in place of voltage source we will get current source, so it is in series resistance we will get parallel resistance, right? Now we should know how to find VTH, RTH, or IN and RN, right? So otherwise we cannot find. So there is some standard procedures to find, right? So if I do one example it will be clear actually, right? Now we will see through this example how to find VTH and RTH. Now remember, see, this is the same problem we have done for the superposition theorem. Now we will do with this Thevenin theorem, and we will see that the current I is same or not. Now to find VTH, RTH, or IN or RN, wherever we need the response, so just open this resistance there, just open the either load or current source or whatever, just open that one. Now when I open that one, so it will become like this: 5 volt, this is 1 ohm, this is open, this is 3 ohms, this is the 2 ampere current. Now wherever we open, give a voltage VTH. Now once we find the VTH, how to find the VTH? See, at this node, this is the grounded, so it is nothing but VTH. If I apply nodal analysis or KCL, VTH minus 5 by 1, see, this current is incoming. If I assume this is, we assumed as outgoing, so this is minus 2 is equal to 0. What is VTH? Simply 7 volt, right? Now how to find RTH? Now to find RTH, right, make all independent sources 0. Make all independent sources 0, right? So make all independent sources 0, that is current is 0, that means open circuit, voltage is 0, that means short circuit, and find R equivalent, right, where we opened the resistance, right? So that is how to find this R equivalent. So if I draw like this, see, this is the voltage source, we need to make short circuit, right? Then there is a 1 ohm resistor. Now see, this is the where we need to find, because we opened this one. Next here, this is 3 ohms, and here there is a current source. So whenever there is current source, it will become open circuit, voltage source, this is becoming short circuit. Now we have to look here, this is the R equivalent or RTH. Now if you see here, this is anyway open circuit, so current through this resistance is 0, so it will be eliminated. So simply this R equivalent or RTH is nothing but simply 1 ohms. Now how to model this one? See, so this is a VTH, and VTH we got 7 volt, and series resistance we got, this is 1 ohm, and where we left, that is 2 ohms here. Now what we need? The current I. So if you single loop, I can find simply I is equal to the voltage by the resistance, 7 by 3 ampere. So whatever we found in the using superposition theorem, this is also same. Now how to find this equivalent Norton? So once we find VTH or RTH, then we can make this source transformation, that is minus is there, so it is going up, so 7 ampere, and this is 1 ohm, and this is 2 ohms. Now to find again by superposition theorem, not superposition theorem, current division principle, I is equal to the main current into opposite resistance by total resistance, so 7 by 3, we get same answer. but this is not actual procedure. So actual procedure is another way. So finding R equivalent is same. So R equivalent is equal to Rn is equal to RTH. To find R equivalent, same procedure will go. Same procedure to find Norton equivalent procedure. But to find In, now how to make? So wherever we have to find the response for VTH we open. Now we make short circuit and find the current. That is like this. So this is the 2 ohm resistance. Now we will make the short circuit, and this current is making as ISC. This is 1 ohm, this is plus minus 5 volt, this is 3 ohms, this is 2 amperes, right? Now how to find this ISC here? Now again, what is the voltage here? This is the 0 volt. But the moment it is short circuited, this is 0 volt, right? Now this is 2 ampere is incoming, this is 2 ampere, and if I find this current here, see, this is 0 and this is 5, so 5 voltage is here. So always current flows from higher voltage to lower voltage. So if this is if I assume some current I1, so I1 is equal to 5 minus 0 by 1, so 5 ampere. That means this 5 ampere is also incoming. Now what is ISC now? ISC is incoming is equal to outgoing, so 5 plus 2, so 7 ampere, right? See, always we have to assume the current direction is in the downward, then only the equivalent model will be upward like this, right? So IN is equal to ISC is equal to 7 ampere. Now what is the R equivalent? So R equivalent procedure is same I told. So this is 1 ohm only. Now wherever we have to find response, that resistance again I is equal to 7 by 3 amperes. So this is about the Norton equivalent and Norton theorems or Thevenin's theorem, right? In the next lecture we will see some problems on this theorem, superposition theorem, Thevenin's theorem, etc. Right?